Think about the really complex, expensive kit that keeps things running. Aircraft, big ships, or those huge wind turbines you see out in the fields.
Massive engineering project.
Exactly. And they're designed to last for decades, often in really harsh conditions. But things inevitably degrade over time, performance drops.
And that means high maintenance costs, right?
Yeah.
Plus the risk of unexpected breakdowns, which can be, well, disastrous.
Precisely. And that's where something called prognostics and health management PHM comes in. It's the whole system for monitoring, diagnosing, and predicting the health of this equipment.
It's absolutely vital, PHM. But the thing is, most current systems are mainly focused on the physical asset itself. There's often not much of a link, or at least not a deep, real-time link to a virtual counterpart.
Ah, okay.
And that's the gap the digital twin fills. It's really a game changer here. People call it a digital mirror. Basically, it's a very detailed virtual model designed to perfectly merge the physical world with the virtual one continuously.
Okay, a digital mirror. I like that. So let's unpack that. How does this mirror idea actually, work to keep machines healthy and stop those expensive failures?
Right?
Our mission today is really to get into this five-dimension digital twin model and see how it powers better PHM.
Okay, so the core idea is simple enough.
Yeah.
The digital twin is a living virtual copy that's always talking to the real physical thing.
A living copy.
Yeah, constantly interacting.
Yeah.
Now, the source we looked at builds on this with a specific five-dimension model. It
Yeah.
really breaks down what makes it tick.
5 dimensions. Okay, what are they?
So first, you've got the physical entity that's the actual wind turbine, say, with its blades, gearbox, sensors, everything.
The real thing. Got it.
Second, the virtual equipment. This is the high-fidelity digital model. Think detailed 3D geometry, but also its physics, how it behaves, the rules it follows, like a simulation showing how the blades might deform or the stress on the gears.
So much more than just a picture.
Oh, absolutely. Then third, you have services. These are functions, like software services, that help optimize the real equipment and also keep the virtual model accurate, maybe a service monitoring power output, for example.
Okay.
Fourth dimension, DT data. This is crucial. It's not just raw data. It's data from the physical machine and data from the virtual model and data from those services plus domain knowledge all fused together.
Fused data. Interesting. So it's richer information.
Exactly. Much richer for doing the health management part. And finally, fifth, the connection.
Yeah.
These are the links, the communication pathways, making sure everything talks to each other in, ideally, real time, sending sensor data one way, getting model updates back the other way.
Okay, that 5-part structure makes sense. Physical, virtual, services, data, connection. But
Right.
here's the key question, right? How does having this complex digital mirror actually drive better prognostics? How does it change the process?
Right. It changes the workflow fundamentally. Our source breaks it down into 3 stages. First is observation.
Observation.
Yeah, this is about setting up the digital twin initially and then constantly calibrating it, making sure the virtual model stays a true reflection, a real mirror of the physical one.
Keeping it accurate. Makes sense. What's next?
Stage 2 is analysis. This is where the system does what's called consistency judgment. It's always comparing the state of the physical machine with the state of the virtual one.
Checking for differences.
Exactly. And if they start to drift apart beyond a certain acceptable limit, the source mentioned maybe 6% for a wind turbine, the system needs to figure out why. Is the real machine degrading slowly? That's a gradual fault. Or did something sudden happen, like a big gust of wind, an abrupt fault?
Okay, so it flags a mismatch. And that then raises the question, how does knowing there's a mismatch help predict faults better?
Well, because the digital twin isn't just using, say, a single vibration sensor. It's using that fused data we talked about, physical sensors, plus the physics-based virtual model, plus historical data. This allows for, frankly, much more sophisticated identification of why things are deviating.
Ah, I see.
It can pinpoint the likely cause much better, whether it's wear on a gear tooth developing over time or something else entirely. It gives you a much clearer picture for prediction.
Right. And then you get to the decision stage, the maintenance part.
Precisely. The system suggests maintenance actions. But, and this is really cool before anyone picks up a wrench, the proposed maintenance strategy is first tested on the virtual equipment.
You simulate the fix.
Simulate the fix, you check if it will actually solve the problem and if it has any unintended consequences, all in the virtual world. It minimizes risk, avoids unnecessary downtime, saves money.
Wow. Okay, that's a huge advantage, testing the repair virtually first.
It really is. And think about that data fusion again. Take the wind turbine gearbox example. Traditional methods might just look at vibration signals from the physical box.
Which can be noisy or misleading sometimes.
Very prone to interference, yeah. But the DT method, it fuses that vibration data with, say, stress analysis calculated from the virtual gearbox model. You get a much more robust signal.
So the takeaway seems pretty clear then. The source indicates that for something complex like that gearbox, this DT approach was significantly more accurate at predicting problems, things like tooth wear, fatigue, breakage, compared to the old ways.
That's what the comparison showed. Yes, a definite improvement in accuracy and reliability.
So boiling it down, for industries with these big, expensive assets, digital twins aren't just hype. They offer a real, practical way to get much more accurate, much more reliable health management.
Absolutely. And that translates directly into cost savings, less downtime, and importantly, better safety by catching potential failures earlier.
Makes sense. But it can't all be straightforward, right? What are the hurdles?
Good point. While it's incredibly powerful, scaling this up has challenges. You need to build these high-fidelity models for all sorts of different equipment, which takes effort and expertise.
Right.
Then there's handling the sheer volume of data these twins generate. And, of course, the initial investment, building the twin, setting up the systems. You have to balance that cost against the long-term savings.
So, promising, proven for critical stuff, but scaling has its complexities.
That sums it up well.
Okay, let's leave our listeners with this thought. Think about the complex machines just in your own life. Your car, maybe. Or even the infrastructure in your city. The power grid, the water systems. What if they had digital twins monitoring their health? What could that reveal, and how might it change how we maintain, well, everything?